Section 13.2, integrals or antiderivatives of vector value functions, and a couple of applications. Given the vector value function ft, gt, and h of t in R3, it could be also in R2, it doesn't matter. The antiderivative of vector value function is antiderivative of each of these components. You know, the x component, y component, and z component, which they happen to be functions of t. So there are two kinds of integrals, just like real value functions. Either the integrals are indefinite or definite, meaning either t has no limits, or the integral has no limits, or it does have a limit. However, in order to take the integral of a vector value function, as I mentioned, you take the integral of each component, and each time you get an antiderivative, you get a constant. Do you see it? So here you get capital F of t c1, capital G of t c2, capital H of t c3. However, I can rewrite this as sum of these two vectors, and lo and behold, the answer is a vector which contains all the antiderivatives of those three functions plus c, but notice c is a vector. Do you see it? So the constant of integration for integrating the vector value functions is not a number, it's a vector. Do you see it? In case you have a definite integral, like let's say evaluate, let's say r of t dt when t goes from a to b, get the antiderivatives, there's no need for c. Evaluate this between what? Upper and lower limit. First you evaluate it at the upper limit, minus evaluate it at the lower limit. At the end of the day, the answer is still what? Vectors. So in other words, you get fb minus fa, gb minus ga, and hb minus ha, but it's a vector. So the answer is still a vector. Do you see it? The next idea is, let's do an example so we can see this in action. Here is r of t, which is cosine of t sine of t. Remember, that's your infamous curve helix. Okay, find the antiderivative in general, and then find the same antiderivative evaluated to what? T goes between 0 and pi over 2. Remember, we take the antiderivative with respect to t. So this would be antiderivative of cosine, which is sine, antiderivative of sine, which is negative cosine, antiderivative of t, which is t squared, but don't forget the constant, which happens to be a vector, correct? On the other hand, if I was going to evaluate this definite integral, I still get my what? My antiderivative, okay, but I don't need c anymore, so I'm going from 0 to what? Pi over 2. So the answer would be, let's say 1, 0, pi squared over 4 minus 0, negative 1, 0. Evaluate these three functions at 0 and pi over 2. First at pi over 2, then at 0, then subtract. You know, fundamental theorem of calculus. So this would be 1, this would be like 1, and that would be like pi over 2, pi squared over 4. Notice in either case, the answer is a vector, but in case 1, you get a vector plus additional vector c. This kind of sort of the idea behind solving differential equations. What kind of equations are called differential equations? The type of equations which you have what? Derivative in it. Notice this is called a differential equation involving vector value function. The objective of these kind of problems is to find the original function, and then because we're going to end up with a c, so this is called initial condition, right? And this is usually given so we can find out what exactly c is. Remember, you're going to get a constant of integration. So to find r, All I have to do is take antiderivative of r prime, which happens to, with respect to t, of course, which happens to be antiderivative of 3/2 t plus 1 to the power of 1/2 e to the power of negative t 1 over 1 plus t dt. Keep in mind, the idea is to take the antiderivative of these guys one at a time. So that would be like 3/2 times what? T plus 1 to the power of 3/2 times 2/3 negative e to the power of negative t, and the last one is natural log of 1 plus t. Don't forget the c. So this is your r of t in general, correct? But remember, we are given initial condition. When they say r of 0 is k, what they mean by that is when you replace the t's with 0, you get unit vector along the z-axis, which is k. In other words, I and j happens to be 0, so this is a unit vector. So what you do, you impose this condition right here in this last equation to find out what c is. How do you do that? Replace r of t, r of 0 with 0, 0, 1, and replace what the t's with 0, because that's what this guy is. Okay, here you get 1, here you get negative 1, e to the 0 is 1. Natural log of 1 plus 0, natural log of 1 is 0. This is plus c. So therefore, c is equal to 0, 0, 1 minus, move this vector over to the left side, subtract these two vectors, and lo and behold, you get negative 1, positive 1, and 1. So c is what? Negative 1, 1, 1. So remember, c is a vector. What do you do now? You go back to the equation inside the box, replace the c with this guy. So r of t is equal to what? T plus 1 to the power of 3/2 minus e to the power of negative t, comma, natural log of 1 plus t, and then plus negative 1, 1, 1. So now you've got two vectors, which the job is to add them up. How do you add two vectors? You add the x components. So this is t plus 1 to the power of 3/2 minus 1, comma, negative e to the negative t plus 1, comma, 1 plus natural log of 1 plus t, but the final answer is still a vector. In other words, you can write the answer as t plus 1 to the 3/2 minus 1i plus minus e to the negative t plus 1j plus 1 plus natural log of 1 plus t k. If you like to write the final answer as linear combination of what? I, j, k special unit vectors. Okay, so the question is, why do I care about taking the antiderivative, correct? Well, the idea is as follows. Remember when you had a position vector, you take its derivative, first derivative, you get velocity. Is that right? Velocity. You take its second derivative, you get what? Acceleration. Acceleration. What if you know the acceleration and you want to go to the position function? So how would you do this? Well, the answer is to go from acceleration to velocity, you take antiderivative of acceleration. And to go from velocity to position vector, you take antiderivative of what? Velocity. Do you all see it? So antiderivatives is used in what? In as opposed to derivative. So to go from position vector to acceleration, we take consecutive derivatives. But to go from acceleration to position, now we have to take antiderivative, correct? For instance, let's say this is acceleration subject to this initial condition, and r prime of 0 is 0. That's like what? Initial velocity. Find the velocity and position vector. So you start from what? This guy right here. Okay. To find the velocity, I need to take the antiderivative of acceleration with respect to what? With respect to t, of course. So you take the antiderivative of this vector, each of these components, with respect to t. And what do you end up with? Don't forget, you get a c. I get negative t, negative t, negative t plus c1. And this is my velocity, correct? Remember, you get two c's, so you are given what? Two conditions. Believe it or not, r prime of z is the same as initial velocity, correct? Which happens to be zero vector, which happens to be, in this case, 0, 0, 0. So I'm gonna use, this is velocity in terms of t. To find c1, I'm gonna apply this initial condition, or the saying goes, let's impose this initial condition to find c1. So I'm gonna replace the v with 0, 0, 0, and the t's with 0, 0, 0. And lo and behold, c1 comes up as a zero vector. So now go back to this velocity function, replace the c1 with 0, 0. So you're going to end up with negative t, negative t, negative t, and adding 0 vector to any vector is still the vector itself. Okay, but now I need to find the position vector. How do I find that? By taking antiderivative of velocity, which is by taking the antiderivative of each of these components. So that would be negative t dt, negative t dt, negative what? T dt. But don't forget, now you have a second what? Constant. Remember, in each case, the constant happens to be a vector, yes? So r of t is equal to negative t squared over 2, negative t squared over 2, negative t squared over 2 plus c2. Now I need to find c2. So this time I need to what? Apply this condition. Believe it or not, this is initial position. Initial position. In other words, r of 0 is initial position. R prime of 0 is the same as v of 0, which is initial velocity. Okay, initial velocity at time 0. So I'm going to apply this condition. So I'm going to replace this guy with 10, 10, 10, because the initial position, you know, when t was 0, the object was at 10, 10, 10. So replace the t's with 0, 0, 0, 0. So it looks to me what? C2 comes up to what? 10, 10, 10. Now go back to this equation, replace the C2 with 10, 10, 10, vector 10, 10, 10. So the answer would be what? Remember, you're supposed to add this vector 10, 10, 10 to this vector. So you get 10 minus t squared over 2, correct? 10 minus t squared over 2, and 10 minus t squared over 2. So this would be like the position vector. How did we get that? By knowing the acceleration, I took consecutive what? Antiderivative. I got to the position vector. However, in the middle of the road, I had to deal with what? Constants. But the constants in this particular chapter, you know, when you are concerned with vector value functions, they are vectors. They are not numbers. Be careful. Okay, finally, we have something called projectile motion. Projectile motion are type of motion in which this type of motion describes how an object is fired at some angle from initial position and acted upon only by the gravity. Moves in a vertical coordinate plane, and there are two assumptions for these projectile problems, okay? One of them is we ignore the air resistance, so that's also known as drag force, correct? The other one is we assume the mass is constant, okay? So Newton's law of motion, Newton's second law of motion says what? The net force acting on a mass is proportional to the acceleration. If there is a motion, there is an acceleration. Okay? So, if the only force acting on what? On the mass is the gravity, so that would be the weight of the object, which is mg, and g is that constant, which is either what? 9.8 meter per second squared in metric system, or 32 feet per second squared in English system, correct? So it's the constant of gravity. Now, why is it minus? So the object has been shot off, and then it is coming down. So therefore, if this is positive, so going down towards the center of the Earth, we're gonna assume this is negative. Sometimes people in physics classes, they go other way around, so it's just a matter of convenience. Okay, so MA, okay, which is the Newton's law of Coulomb, is the same as negative mg. But the masses are constant, so these guys nicely go away. So A becomes negative g. However, we have a problem here. This guy is what? Vector. This guy is a number, so I can't have vector equal to a number. So I have to express this in terms of vector. So what do? I write this as 0, negative g. Because g is going downwards, so there is no x component, so the y component of the vector is negative g. So, or you could just write g as negative mgj. You know, it's the y component of the vector, okay? You know, the gravity. So anyways, once again, the masses cancel, so you get what? Acceleration, which is the second derivative. So this is like second derivative of the position, which is called acceleration vector, is equal to minus gj, which is the same as 0 comma negative j, correct? So to go from acceleration to velocity, I need to take antiderivative of this vector. Remember, negative gj is the same as 0, negative g with respect to t, and then I go find it, and I have to find the constants, just like previous example, and lo and behold, at the end of the day, I have to take one more derivative to get what? To get my position vector, and I have to, of course, impose what? My initial conditions, and that would be it. So to kind of go over this short story, what do you say we do a quick example and then go from there? Here's the problem. The problem is a projectile is fired from an initial speed, or I should say with an initial speed of 200 meters per second. And the angle of elevation is 60 degrees. Can you find the range? Sometimes it's called down range of the projectile. And can you find the maximum height reached by the mass? And can you also find the speed at impact? Impact meaning when the mass hits the ground, what was the speed? Contrary to common beliefs, it's not 0. Okay, so this is what's happening. Obviously, the projectile was done at the ground level. So this is ground level, correct? Excuse me. This is the velocity. Initial velocity, which makes it what? Angle of 60 degrees with the horizontal, okay? So we know the magnitude of the what? Initial velocity is given to us as 200 meters per second. And usually the angle of elevation is shown by alpha, is given by 60 degrees. So I need now to express initial vector in terms of its components. So I have to what? kind of like go, you know, what would be the x component, what would be this y component. So remember, these are not vectors, these are just scalars. So these are x and y component of the what? Of the initial velocity. So you know what to do. This would be like what? Magnitude of this guy, which is given to us as 200 meter per second. So that would be 200 times cosine of 60, and this would be 200 times sine of 60. Cosine of 60, I believe, is 1/2. Sine of 60 is the square root of 3/2. So this would be 100, comma 100 square root of 3. So this is my initial velocity vector, whereas this guy was its magnitude, correct? What do? We always start all these problems from here. Acceleration is equal to 0 minus g, correct? So now to go from acceleration to velocity, I have to take antiderivative of this guy, this vector, with respect to t. What do I get? I get 0 minus gt plus c1. Don't forget, every time you get a constant, it's a vector, because we're dealing with a vector value function. First, my job is to find what c1 is. To find c1, I have to impose this initial condition. Initial velocity is equal to 100, comma 100 square root of 3. So I'm going to replace this guy with 100, comma 100 square root of 3, correct? Then I'm going to replace the t's with 0. Then I'm going to come up with c1 is equal to 100 square root of 3. Then in this equation right here, I'm going to go back to that equation and replace this c1 with this vector. So I'm going to get velocity vector is equal to 0 minus gt plus 100 and 100 square root of 3 and 3. So if you add these guys up, you get what? 100, comma 100 square root of 3 minus gt. So that's your velocity. And this would be so many meters per second. To go from velocity to position vector, now I have to take what? Antiderivative of this guy with respect to t, you know, this vector value function. So what would that be? Well, this would be like 100t, comma 100 square root of t minus g over t squared plus c2. So now I have to find c2. What is c2? Well, the projectile was what? Performed at the ground level. So that means r of 0 is equal to 0, 0. Why? Because the projectile was performed on the ground 0. At time 0, the mass was on the ground. So here is one more condition. In other words, this is called initial position. Where were you when you performed the experiment? Where was this experiment performed? Was it like at the top of a building, or was it on the floor? Where was it? Because it was on the floor, so there was no initial height. In other words, initial condition is at 0, 0 at the origin. So replace this guy with 0, 0. Replace all these t's with 0. Okay, and then find out what c2 is. c2, which is a vector, 0 minus 0 is still 0, so it's 0. So go back here and replace the c2 with 0. So your what? Position function is 100t, comma 100 square root of 3t minus g over 2t squared. So we got our position what? Vector. Now I can answer the following questions. What is the range? A range is how far the mass has traveled horizontally till it hits the ground, correct? So this x component right here is what? X component of the position is the range. So this is down range or just simply range. So I like to find the range. So what would I do? Well, to find the range, I know the x component of the position function is 100t, correct? So to find the range, first I have to find the amount of time which took for the mass to hit the ground. How would I do that? Because in order to evaluate this range, this is the range, which is what? X component of the position vector. So this is position vector. I need to know what time is, right? The time. Which time? The time which took the mass hit the what? Ground. To do that, the y component of the position vector has to be equal to 0. So I'm going to go, okay, if y is equal to 0, what is t equal to? In position vector, correct? So what would I get? I would kind of like what? Solve this equation for t. If you factor out the t, you get 100 to the square root of 3 minus g over t, g over 2, t equals 0. Either t is equal to 0, that's when the mass was on the floor, or it took about what? Oh, I would say 100 to the square root of 3 over 9.8 divided by 2 is 4.9, and that would be seconds. Okay, so let me get a clean piece of paper so I can show you what just happened here. So here we go. What I'm saying is the following. What we have is this. The position vector came up to 100t, comma, 100 square root of 3t minus g over 2t squared. Remember, g is in this case is 9.8 what? Meter per second square, which is the constant of what? Gravity in metric system. In English is 32 feet per second square. The idea is how far this what mass traveled on the floor to go from where it was fired till when it hit the ground. Well, to do that, I need to find the x component of the position vector, correct? But I need to know how long it took the mass to hit the ground. So at this point, there is no y. So I'm going to go back to the y component, right? Remember, x is 100t. That's what I'm trying to find. But the y component is 100 square root of t minus g over tt squared. Okay, in my position vector, this is my y, that's my x. X is called the range. So I need to set this equal to 0 because when the mass hits the ground, there is no height. And solve for t. Either t is equal to 0 or t is equal to 100 square root of 3 over 4.9 because g 9.8 divided by 2 is 4.9 seconds. So it took this many seconds for the mass to hit the ground. So I'm going to go to the x component and replace the t with 100 square root of 3 over 4.9 seconds. When you do, you get what? You get, let's see, roughly 3,000, what? 535 meters. Because this guy comes up to roughly 35.3 seconds, this guy right here. So if you stick that in the x component of the position vector, you get about 3,535 meters. Okay, that's called the range, so that's part A. Part B is, what is the maximum height? In other words, when the mass goes up, at some point it reaches its maximum, then it goes down. So this is where the mass changes its direction from going up to going down. What is this maximum height? This guy right here. What is this maximum height? You see it. How do I do that? To find the maximum height, either I take the derivative of the position vector and set the y component equal to 0, or set the y component of the velocity is equal to 0, because at the maximum, the tangent is 0. The tangent line is horizontal, so it's 0 slope. So one way to do this is to find the vertical, component of the velocity. Remember, the velocity was, what was my velocity? Do you remember? It was, this guy, 100 comma 100 square root of 3 minus gt, I believe. So what is the y component of the velocity? Is this guy, so I'm going to set that guy equal to 0. Okay, and I'm going to solve for t. So when you do, you get t is equal to 100 square root of 3 over g. Is that right? And let's see. And that would give us something like 17.7 seconds. So it takes about 17.7 for the object to reaches its maximum. Now evaluate the y component of the position vector at t is equal to 17.47 seconds. Okay, remember the position vector came up to, what was it equal to, guys? 100t, 100 square root of t minus g over t squared. Here is the y component. So y maximum is 100 square root of 3t minus g over 2t squared, evaluated at time which took the mass to reach its maximum height. And this guy, if you do it correctly, it comes up to 1,531 meters. So there you have it. That's part B. Part C is what's the speed at impact. In other words, when the mass hits the ground, what was the speed? Okay, speed is a scalar, velocity is a vector. So what do? Well, from part A, I found out it takes 100 square root of 3 over 4.9 seconds for the ball to hit the ground. Is that right? So I'm going to evaluate the velocity at that time, which is 4.9. What was the velocity? You remember the velocity was this guy, which is 100, 100 square root of 3 minus gt. Evaluate this at t equals 100 square root of 3 over 4.9 seconds. Go back here and replace this t with this many seconds, and you're going to end up with 100 minus 100 square root of 3. So the x and y components come up to nice numbers. Now, to find the speed, so we are not done yet, that's the magnitude of the velocity at at t is equal to 100 square root of 3 over 4.9, okay, which is the square root of this guy squared plus that guy squared, which is like 10,000 plus 30,000, and that gives you exactly 200 meters per second. So this is the speed at impact. Thank you.